Children, I hope you have gone through my previous video, and today we will continue further. Children, today in the chapter Chemical Kinetics, we are going to study about molecularity of a reaction. Molecularity is defined as the total number of reactant molecules which take part in a particular step or in rate determining step of a chemical reaction. Now till now you have studied about the order of reaction. Let us see what are the differences between order of reaction and molecularity of reaction. Order of reaction is the sum of the exponents in the rate law equation, whereas molecularity is the total number of molecules of reactants taking place in a particular step of reaction. Order of reaction may have fractional values or it may be 0. But molecularity of reaction is always a whole number other than 0. Order of reaction for complex reactions is the overall rate of reaction depends on slowest step, and the overall order is also determined by the slowest step. But in case of molecularity, there is no significance of overall molecularity for a complex reaction. It is expressed for each elementary step. Order of reaction is determined experimentally, whereas molecularity is a theoretical concept. Order of reaction can change with change in temperature, pressure, etc. But molecularity of a reaction is unchangeable, invariable. Okay, next we come to temperature dependence of rate of a reaction. Most of the chemical reactions, their speed is increased by increase in temperature. Even in your labs, you must have seen when you are not getting a result, we tell you to heat the test tube or warm the test tube a bit, and then you get the desired color. So that is because by increasing the temperature, the reaction becomes faster for most of the reaction. For example, potassium permanganate is decolorized at a faster rate at a higher temperature than at a lower temperature. Now generally for a chemical reaction with rise in temperature by 10 degrees Celsius, the rate constant is almost doubled. So you can say that temperature coefficient mu is equal to rate constant at T plus 10 degrees Celsius upon rate constant at T degrees Celsius. According to the collision theory of chemical reaction, rate of reaction depends upon collision frequency. That is the number of collisions which take place per second per unit volume of the reaction mixture, and the fraction of effective collisions or the molecules which after collision produce the products. So the effective collisions take place only in those molecules which have threshold energy and a proper orientation. So increase in rate of reaction with temperature, it is brought about by either of two or a combination of both factors which are being discussed. First is increase in the collision frequency. For every 10 degree rise in temperature, increase in kinetic energy is by 3% only. And second is effective collisions. So the fraction of molecules capable of effective collision, they get doubled at 10 degree rise in temperature. So the rate of reaction gets doubled. You can see here it is shown over here when you plot kinetic energy and against fraction of molecules. So at this point, this is the most probable kinetic energy, because here the chances of collision are maximum. Similarly, in this one, this graph is showing distribution curve of temperature dependence of rate of reaction. So till here, the black portion, it is the area which is showing fraction of molecules reacting at T, and this above the shaded portion, this is showing the fraction of additional molecules which react when the temperature becomes T plus 10. Okay, so on increasing the temperature, the initial curve was this, but when you increase the temperature, the curve became this. And this difference is showing that now the more number of reactants molecules are colliding with each other because the temperature has increased. The next is concept of activation energy and transition state theory. Now we all know that chemical reactions do not take place at room temperature. Some extra energy has to be supplied to the reactions to bring their energy equal to the threshold energy. Threshold energy is the energy which is needed to carry out the reaction. So this excess energy must be supplied to reactants to undergo chemical reaction, and this excess energy is called as activation energy. So actually activation energy is threshold energy minus the average kinetic energy of reactant molecules. So it can be represented like EA is the activation energy is equal to ETH, that is the threshold energy, minus ER, kinetic energy of reactant molecules. This graph here is showing you the different. See, suppose this is the ER is kinetic energy of reactant molecules. This is the kinetic energy of products. Alright. And this is the threshold energy, ET. So, to the reactants, this much energy has to be provided from here till here for the reactant to reach up to the threshold energy level. So this is this, you see this arrow, this is the activation energy, the extra energy which has to be provided to reactant so it reaches the threshold level. All right, and then it forms the products, and the energy of products is this is, so actually the energy of reaction is delta H. This is energy of reactants minus energy of products. All right, so that delta H is the energy of reaction. Now see, fast reactions, they have low activation energies, whereas slow reactions have high activation energies. Now activated complex or transition state is an intermediate complex which is highly unstable due to high energy. When the energy reaches to the threshold level, then the complex that is formed is activated complex. See, A has reacted with B2. These are the reactants. So it has formed an activated complex ABB. Now because it has very high energy, so this is unstable and it will break down into AB plus B, which are the products. So activated complex is intermediate complex which is highly unstable because it has high energy. Now for a reversible reaction, the activation energies are different for forward and backward reaction. We feel na ki they are similar, but it is not the same. Activation energy for forward reaction is different from activation energy from backward reaction. Like you can see for exothermic and endothermic reaction through these graphs that have been provided over here. See here, this first graph is for exothermic reaction. Now see this energy. Now for exothermic reaction, for the forward reaction, this was the energy of reactants, this is the threshold energy, so this is the activation energy of forward reaction, and this is forming the products over here. Okay, now if you go in the reverse direction, then the products become the reactants. Now the threshold level is this, so this energy will become the activation energy. So this is the activation energy for backward reaction. So they are not same. This is not same to this, isn't it? So they are different. This is delta H is the energy of reaction. Now similarly for endothermic reaction, see this is the energy of products, and this has to reach up to the activation threshold level. So this is the activation energy of forward reaction. Products will be formed. This is the energy of products. Now if you go in the backward direction, again the energy of product is less than threshold energy, so this much extra energy has to be provided. So this becomes activation energy of backward reaction. Okay, so you will see over here, in case of exothermic reaction, activation energy of backward reaction is more than the activation energy of forward reaction, whereas in endothermic reaction, activation energy of forward reaction is more than the backward reaction. So it is clear from these graphs that for reversible reactions, activation energies for forward and backward reaction is not the same, but they are different. Next we come to Arrhenius equation. This equation proposes a quantitative relationship between rate constant and temperature, and this equation is given as K is equal to AE minus EA upon RT, where K is the rate constant, A is the Arrhenius or frequency or pre-exponential factor, EA you know is the activation energy, R is the gas constant, and T is the temperature in Kelvin. Okay, the value of A does not depend upon the temperature and catalyst. Two quantities A and EA are collectively called as Arrhenius parameters. The factor e to the power minus EA upon RT gives the fraction of molecules having energy equal to or greater than the activation energy, and it is called as Boltzmann factor. Okay, now in this log, if you take log of both the sides, so log K is equal to log of A minus EA upon RT. Okay, so 1 second. So taking log of both the sides, log K is equal to log A minus EA upon RT. So if you take log to the base 10, it becomes log K is equal to log A minus EA upon 2.303 RT. This you have to remember because in the numericals you will be using this formula. Okay. Next, if we take two different reactions, suppose K1 and for two different reactions, the rates will also be different. So suppose there is first reaction has log K1 is equal to log A minus EA upon 2.303 RT1. Temperature in first reaction is T1. Similarly, log K2 will become equal to log A minus EA upon 2.303 R is constant T2. Okay. Now from both these equations, when you subtract them, you will get log, subtracting the second one from the first, first one from the second, you get log K2 minus log K1 is equal to log A minus EA upon 2.303 RT2 minus log A minus EA upon 2.303 RT1. So you get log A upon log K2 upon K1 is equal to EA upon 2.303 R 1 upon T1 minus 1 upon T2. Okay. So from this equation you can calculate EA if you know the temperatures and the rate constant. Next is calculation of activation energy. So these equations you have to learn by heart because you will be using them in the numericals. Next is calculation of activation energy by graphical method. Now for calculating activation energy by graphical method, the formula See here, you have plotted 1 upon t on x-axis and log k on y-axis. Okay, now the slope of this is given by minus EA upon 2.303 R. So you can calculate activation energy by the formula of log K is equal to minus EA upon 2.303 RT plus log A. Alright. So from this you can calculate by graphical method as well. Next is, this will represent log A and the slope represents minus EA upon 2.303 R. Okay. Next is effect of catalyst on reaction rates. Now the substances which affect the rate of reaction and can be recovered chemically unchanged in mass and composition after the reaction is over are called catalyst. Catalysts do not get used up in the reaction, but they help to increase or decrease the rate of reaction. So it does not shift the position of equilibrium. Catalysts are highly specific in nature and does not change delta E or delta H or delta G of the reaction. Okay, so see over here through a graph they have tried to explain process of an uncatalyzed and catalyzed reaction. So addition of a catalyst provides a path of lower activation energy. See here the graph. There are two curves over here, this and this. Now the lower one, this is if you add a catalyst to the reactants, it will decrease the threshold energy. So the reaction will be faster. But if it is uncatalyzed, first for the reactants to reach up to this point and then the products to be formed, it takes a longer duration. So basically what the catalyst is doing is it is lowering the activation energy. Products formed are the same. Only thing is in one case it will be faster and the other one will be slower. Next is effect of catalyst on activation energy. Now suppose the rate constant of reaction in the absence and presence of catalyst, if it is K1 and K2. K1 in absence of catalyst and K2 in presence of catalyst. Now as the catalyst lowers the activation energy, therefore E1 will be greater than E2 and K2 will be greater than K1 if the temperature is constant, because E1 is without the catalyst and E2 is with the catalyst. So activation energy without the catalyst is more and with the catalyst is less. So E1 is greater than E2, and for the rate also K2 will be greater than K1. So you get the equation log K2 upon K1 is equal to E1 minus E2 upon 2.303 RT, or can be written as log K2 upon K1 is equal to delta E upon 2.303 R3. Now if EA is the activation energy of reaction at high temperature T1 and E dash A is a decrease in activation energy barrier after adding catalyst at a lower temperature T2, then EA upon T1 is written as is equal to EA minus E dash A upon T2. Okay, and in this case T1 and T2 should be taken in Kelvin. If they are in Celsius, you convert them first into Kelvin and then do your calculations. So this is all about the chapter chemical kinetics. I've taught you the theory portion. You will have to practice the numericals. These are the formulas which have to be used. Just see the questions that are given behind the book and try to apply the formulas in your numericals. You'll have to make use of logs. tables, all that you already know how to do it. Okay, try it out. That's all for this chapter.